Hello, this is video 13, lucky number 13 for lucky module 2 and lucky 2020. What could possibly go wrong? Let's, you know what? We're going to be doing some math, so all sorts of things could go wrong. Let's look at some binary addition. Why do we care? Well, we are trying to get in a computer mindset. We're trying to get inside the mind of the computer. How are you doing what you're doing? Well, the computer would answer, I'm doing it all in binary. That's all I know, zeros and ones. So if we want to know how a computer adds two numbers, we need to look at the binary addition and see whether or not we can think like a computer in that sense. I'll do this strictly by example. Suppose we want to add 55 from base 10 and 19 in base 10. I bet we could do that. We might even be able to do that by hand. But let's pretend that we don't know, question mark, whoops. So we're going to ask the computer to do it for us. The computer will do it for us, and very quickly, but it won't do it as a 5-5 and a 1-9. It will do it as binary. So step one is going to be to get it in a form the computer can understand and operate with. Here we go. We actually got to use the conversions here. Going from decimal to binary, 1s, 2s, 4s, 8s, 16, 32, 64, 128, and that's plenty. Dot, dot, dot. There are more place values. That's all I'm going to use. I'm going to color code this to see if that helps any. It might hurt, but I'm going to see if it helps. Instead of black 55, this is going to be brown 55. Because I'm going to reuse this place value chart. That's the real reason I'm lazy. I don't want to have to keep drawing that place value chart over and over again. So I'm going to color code it. You don't have to do this when you're doing your own version, but I am what I am. 128, can I get any 128s out of 55? Cannot. Can I get any 64s? Cannot. Can I get any 32s? Yes, I can. I can get a chunk of 32 out of the 55. And here's that conversion thing going on. We've got scratch work over here. How much of the 55 is covered by that single one right there? 32 of that 55 is covered by that single one right there. Subtract 2 from 5, I get 3. I made it easy on myself this time. 3 from 5 is 2. So there is 23 marbles, or whatever you want to think of them. There's a quantity of 23 that is yet unrepresented on the place value chart. What about 16? Can I get a chunk of 16? Yes. Yes, you can. 16, subtract that. 16, 17, 18, 19, whoops. 6, 7, 8, 9, 10, 11, 12, 13, 5, 6, 7. 7. There's 7 left. That's not represented by those two ones. So chunk of 8. Can I get a chunk of 8 out of 7? I don't think so. What about 4? Yes, I can get a chunk of 4. Chunk 04 comes out, and put a 1 right there. And subtract, we get 3. I get a chunk of 2. Get rid of that 2. Got 1 left, chunk of 1. Subtract the chunk of 1 for completeness, and done. The number is completely represented, and that is in base 2. Now, by convention, it's hard for me to resist this. We never, or almost never, when we're thinking computer and binary and all that, work with irregular lengths of binary numbers. It's always going to be probably some multiple of 4, because we want to be able to handily go back and forth between hex and binary. We're just smart that way. Here's a chunk of 4 up to there. This, I'm going to need 2 leading zeros. There. 2 chunks of 4 in a row, and I'm done with brown. That's 55. Done and done. 19. Pull the same tricks with 19. I'm going to change the color to blue. That's blue, not black. Those might look the same in the video. I'm sorry about that. But that is a blue 19. Take my word for it. And we do the same thing. In the scratch work down here, I start with the whole 19. How many 128s? None. But since I also want to end up with 8 bits, I'm going to put a blue 0 there. No 128s out of 19. No 64s. No 32s. Yes to 16. 16 is the first yes. And the reason I'm subtracting over here, even though this is supposed to be an addition problem, I'm trying to find out how much more of my number remains to be represented by this bit pattern. 16 of this has already been represented, so only 3 has not yet been represented by that binary bit pattern. How many groups of 8 can I get out of 3? Not any at all, nor 4, but I can get a group of 2. I can get a 2, so I almost put a 2 there, that's got to be a 1. That 1 means I'm taking out a chunk of 2, that leaves the chunk of 1, put a 1 there, chunk of 1. Now, the 0 means everything that was in that 19 is now present and represented in the binary number. Okay? Now then, since math of any sort might be alarming and frightening and everything, and it seems appropriate, especially in video 13, to use red to come up with the answer. And I think I'll do that. But first of all, so that I can still, believe it or not, I'm going to keep reusing that place value chart. I'm going to bring my scratch work down here, reopen the colors, and just copy these numbers down here to my scratch work area so I can add them up. 0, 0, 1, 1, 0, 1, 1, 1, base 2. That was our 55. The blue is 0, 0, 0, 1, 0, 0, 1, 1, base 2. Then the math stuff, stressful, alarming, and red, add those up, plus, and draw a bar underneath it, because I need to add those up to find out what the sum is. Can I do it? Well, do you remember how it seems so far long ago, doesn't it? Far long ago, far go along. It seems so long ago when we were actually just doing plain old simple arithmetic in base 10. Now we're in base 2, but the same arithmetic rules hold. And here's what I mean. When you add 1 plus 1 and you get 2, you don't get to put a 2 down here. When you reach the name of the base, that means you're going to have to carry over to the next column. We don't have to go very far to get to the name of the base in base 2, do we? 1 plus 1 is 2, but a 2 in base 2 looks like a 10. It's a 1 in 2's place and a 0 in 1's place. So what we have to do is put a 0 in the answer and carry a 1 to the next column. Yikes! Looks weird already, doesn't it? 1 plus 1 is 2, but that means put a 0, carry a 1. If you thought that was weird, 1 plus 1 plus 1, that's 3. Everybody knows that's 3. But a 3 in binary looks like an 11. It looks like 1, 1. So we've got to put a 1 and carry a 1 to the next column. I told you it was weird. 1 plus 1 is 2, plus 0 is still 2, but I got to put a 0, carry a 1. Finally, mercifully, I get an easy column. 1 plus 0 is 1, for crying out loud, and carry nothing. There. We either carry a 1 or we carry nothing. What about the next column? 1 plus 1, that's 2. Put a 0, carry a 1. 1 plus 0, that's 2. Put a 0, carry a 1. 1 plus 0 is 1. Carry nothing. I'll put the carry. I'll put this carry 0. Goose egg, goose egg, goose egg. Add 0 plus 0 plus 0, I get a 0. Now, if I did this wrong, first of all, if I did it wrong, I'm probably going to have to repeat the video all over again, and you're not even seeing this. But if that's correct, how do we even know? If that pans out, you know what? I'm going to draw a line here, a double line. Otherwise, it's going to look like another addition problem. That just means I'm too lazy to redraw the place value chart. I'm going to slap this thing on the place value chart and convert back to base 10 and see what we have. That's why I wanted to have like 2 or 3 in 1 place value chart. 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, base 2. Now, the addition is done. We hope it's right. The scratch work conversions are done. So now all we got to do, our finishing touch, is to see whether or not we believe that, whether or not that's the answer we expected to get. 0 times 128. This is back to converting from binary to decimal. 0 times 128 plus 1 times 64 plus 0 times 32 plus 0 times 16. And I started too far to the right. Plus, I'm going to say this is answer, A and S. Answer equals that. Make it more dramatic. 0 times 16 is how far I got. 1 times 8 plus 0 times 4 plus 1 times 2 plus 0 times 1. It's still too early to see whether or not we believe that's the right answer. Do all the little multiplications inside parentheses. That's 0, so I'm just going to leave that out completely. 64. 1 times 64 is 64 plus 1 times 8 plus 1 times 2. Is that it? 1, 2, 3. Only 3 things to add up. Looks like. And since I can't add horizontally, I'm going to have to put it vertically. Scratch work again. 64, 8, 2. Now, a more natural alignment for me. 8 plus 2, I can do that. 10. 10 plus 4 is 14. Put a 4, carry a 1. 6 plus 1 is 7. 74 back in good old base 10. Now, how do we know whether or not we did our binary stuff right? Let's check it back in our more comfortable number system, our more familiar number system. Let's try this. This is not going to be unknown anymore. Let's get a real live answer here. 9 plus 5, I can do that. 9, 10, 11, 12, 13, 14. See? Carry a 1. 5 plus 1 is 6 plus 1 more 7. By Jove, it looks like we did it. We did it. Yay. I guess that's a nice place to quit while we're ahead. It works. That's how you do binary addition. Several steps. You start with your base 10 numbers, convert each of them separately into binary, do the binary addition column by column that I've already erased so I could reclaim the board space. When you get the answer, convert the answer back to base 10 so you can double check and make sure you got the right answer in binary that you would expect from your base 10 math problem. That's how the computer would add those two together, one column at a time, using nothing but zeros and ones, and still gets the expected answer. It's a miracle. I'll see you online.